Again, this is not a question you have to remember, but just to show how to proceed. This is the four-dimensional Einstein tensor. We project it with twice with the timeline projection operator, and that's what we get. And if we equate to the timeline component of the stress energy tensor, we finally get this equation where all the components are three-dimensional, and this is called the Hamiltonian constraint equation because it measures something like, well, it's a zero or timeline component of the constraints. It's something like energy. It is a single elliptic equation, so no time derivatives. Then we can project the Einstein tensor one time, one index in the timeline with the timeline projection operator, and one time with the spatial projection operator, and we get other equations, four other equations, which are called momentum constraint equation because they relate to the momentum. And these four constraints are necessary and sufficient to describe the space, like each space like hypersurfaces, and how these are embedded in the four-dimensional space-time. Okay, so these and Hamiltonian constraints don't contain any time evolution. They, however, describe physical configurations that are solutions of the Einstein equations. So solving this this constraint equation give usually the initial data for our simulations. Then what we're left with is to find the direction of time, the direction for evolutions to teach, to tell computer algorithms to advance in time. The most general vector that connects 2 points onto hypersurfaces is this vector T mu, and that is made of a part that is perpendicular to the hypersurfaces, normal to the hypersurfaces, and a part called beta that is inside one single hypersurface. Beta is called the spatial shift in T because it shifts points inside the spatial hypersurface. And right, so it's important that in our in simulations, in numerical algorithms, all the points that are on a hypersurface, on the next time step, they are all on another hypersurface. Okay? So you see how important it is to choose alpha and beta. Just keep in mind this picture will appear again. Okay, now if T is n alpha n plus beta, then the Lie derivative with respect to a vector n is related to the Lie derivative with respect to T and beta in this way. It's just a vector composition. So the definition of the extrinsic curvature was this on our previous slide. Now instead of n, we change this n to t. So we have the Lie derivative with respect to this t, which is t is the real change that we have. That includes both the time advance and a shift. A shift is possible. Right? It's not necessary, but it's possible. And we have to allow for all coordinates in general relativity. You cannot prescribe the coordinates a priori. So maybe in some application beta will be 0, okay? But in general, it may also not do 0. That's why we have to keep it to the end. Okay, doing that, the time derivative of the spatial metric is then this expression. So it depends on the extrinsic curvature and on some space derivative of the spatial metric. And this is one of the equations that we can tell computers to solve. These equations is completely on a hypersurface, 3-dimensional spatial hypersurface. Then, finally, we can take again 4-dimensional Einstein tensor. We project both indices with the spatial projection operator, and we find this very long equation which tells us what is the time derivative of the extrinsic curvature. And the extrinsic curvature is related to the time derivative of the metric. Okay? So we have all we need for the evolution now. We have two sets of variables with their first derivatives. Finally, fourth and the last step, we have to select a coordinate basis. Up to now, we've explicitly not thought of coordinates because everything needs to be covariant and not coordinate dependent. But to have computers make computations, we need to select coordinates. And a very natural one is the choice of 3 purely spatial coordinates with unit vectors, like digit, and 1 coordinate unit vector along the vector t. We put this coordinate basis into the equations we found, the Lie derivative becomes partial derivative, and this is a description of the timeline components and space-like components, and this is the explicit expression of the normal to the hypersurface. One overlaps, and then it's a vector, 4-dimensional vector, 1 minus beta I. And this is with the index up, and this is with the index down. The 3-metric, the spatial 3-metric, we have defined it as the gamma. So finally, the 4-dimensional metric is split in this way. The spatial components are here, the time 0, 0 component is here, and the mixed time-space components are here. This is valid for the coordinates that we have chosen. Of course, we chose coordinates that are helpful, are simple for making computation. And here is the inverse of that. Now, maybe we can have a more intuitive interpretation of the lapse and shift and spatial metric. In particular, as I was mentioning, the lapse measures the proper time. If you put x equals 0 and beta equals 0 into the interval, you find the proper times. So alpha is the proper time, and the shift instead lives only in hypersurfaces and changes coordinates inside the hypersurface. And the spatial metric is the spatial. So, summary of how to solve 4-dimensional equations in 3 dimensions plus 1 with computers. Oh, by the way, this method is called the ADM, Analytic formulation. Of course, very famous. First step, foliate the four-dimensional spacetime into three-dimensional spatial hypersurfaces with some parameter that we call time, labeling each of them. Second step, decompose all four-dimensional spacetime tensors into their spatial and time-like parts. Third step, rewrite the Einstein equations using this decomposed tensors. And the fourth step, select the coordinate basis and express all equations in the 3+1 or ADM form. Questions up to here? No? Right. Okay. So, I mentioned that laps and shifts are very important for numerical simulations. And here is one. So laps and shifts are related to the coordinates we've seen. So they cannot be important for physics. Physics cannot depend on coordinates. And since they are coordinates, they cannot be thought as gauge conditions. You change them and the physics doesn't change. And as gauge conditions, we are free to choose them. However, I will show you in a minute that not any choice of laps and shift is good. Most choices are bad. And it's indeed an art of choosing these conditions so that they even have a name. So lap is called the slicing condition and shift is called the special gauge condition. And one would think that a very, very simple, straightforward idea is to take alpha equal 1 and beta equal 0. I'm sure you thought of that. However, that's definitely not a good idea. And I'll show it to you in this graph. Here you have, this is a space-time diagram. You have space here and time here. And think of a computer solving this. So we have a grid, a numerical grid that for each point of space has a value of the metric, of the specific curvature, and the other quantities you might need. Okay? And this is time equals 0, the initial time. Then your algorithm produces a time and the solution at the next time, and so on. Okay? That is the standard thing. But in general relativity, singularities appear. So a black hole has formed here. Now we have a physical singularity at some point on the grid. And when your algorithm gets you to the point where there is a singularity, it tries to make a computation with infinity and the code crashes. End of the story. And this is why it took so long to have successful numerical relativity simulations. Because standard things fail to work. Okay, so what can we do? We can be more clever with the choice of games. We can do something like this graph, where again, these black lines that you can probably barely see, I'm afraid, are a given time step in your algorithm, in your computer code. Okay? So you see that they are no longer straight lines. They are bent. And they are bent in a way to allow the time to flow with some speed when you're far from the singularity. But they don't advance much in time near where the singularity will appear. So that, well, if you're clever enough with your gauges, you can contrive one so that the points near the singularity near where the singularity would form will never reach the singularity. So there will never be an infinity on your grid, numerical grid, and so hopefully your code will not crash. Fine? If you're convinced of this, this is important. So if you have questions, you ask now. Okay? So choosing alpha in a clever way allows us to continue the evolution with our algorithm. Because even if there is a physical singularity, it will not be reached in our code. Because the time flows very slowly here, so that it never reaches the singularity, while it flows with some reasonable speed far from the singularity, so that we can proceed with our simulations and compute gravitational waves.
By the way, so in this case, we know that the singularity, right? So you are hiding the singularity somewhere.
Okay,
I mean,
see
the slide
what you think. So in this example is, for example, for a collapsing star.
Yeah.
Yeah, so yeah, there is no singularity at the beginning, and it will form sometime. Is that what you were asking?
My point is that we know definitely the singularity in a black hole, right?
There is a singularity.
The slicing, the two slicing must be related by some gate transformation, right?
You mean this and this?
Yes.
Oh, well, you can think like that. And
Yeah, so the singularity, this must hiding in some gate transformation. I just wonder if this is relevant in the evolution or not. Or I mean, is it always possible we can find such kind of a nice slice?
Well, it turned out to be possible. That's why nowadays we can make black hole simulations. I don't know if this was